My name is Caiqin Dong. I'm a PhD candidate from Jina University. I'm excited to present our work, Fusion, efficient and secure inference resilient to malicious servers. Fusion is joint work with Professor Wang Jian from Well Company and other colleagues. I've divided my presentation into 4 parts. First, I'd like to introduce some background information about machine learning as a service. Then, I'll describe the motivation and design goals of this work. Next, the most important part is our solution, Fusion, for achieving our goals, followed by the performance evaluations. First, I'd like to begin with the real-world applications of this work. As the fast development of artificial intelligence, such as deep learning, machine learning as a service is rapidly emerging in the past few years. In this paradigm, the clients now do not need to train their own models, but consume the services on demand. As we know, training a good model is always computationally expensive and requires large data sets. For instance, now a patient can provide raw medical data to a server, and the server then generates diagnosis results using the pre-trained models. However, in real-world applications, a server may be malicious. For example, a server returns the client random results to trick the clients. These inaccurate results can have grave consequences like misleading patients. In such a worst scenario, in order to obtain accurate inference results, the client wants to verify whether the server used a high-quality model and correctly followed protocol simultaneously. In addition, the client's input data may be highly sensitive, like dynamic data. So the client wants to protect his data as well. Therefore, this paper aims to propose a solution for secure inference that satisfies all 3 design goals, including privacy preservation of both parties, verification of maliciously, and computation correctness at the same time. To our best knowledge, there is no solution that can satisfy all the goals mentioned above. To achieve these goals, there could be multiple ways. For example, we can directly apply maliciously secure 2-party computation to perform inference. Maliciously secure 2PSC protocols can preserve privacy and ensure computation correctness, but extra expensive cryptographic proofs, like zero-knowledge proofs, are required to verify model accuracy without rebuilding the model. Alternatively, we can make changes on existing efficiency and honest inference schemes to achieve malicious security. It's also challenging to customize them to meet all 3 design goals effectively, especially verification of model accuracy. Fortunately, we observe that in a machine learning scenario, the client can know the computation results of some inputs in advance. The known labels of public samples are the expected computation results. These pre-collected public samples with known computation results can be used to verify the model accuracy by comparing the actual outputs with the expected outputs. In particular, known outputs in advance is possible, since there are samples even if healthcare data where both inputs and outputs are publicly available, such as TCGA and NCBI databases. The key question now becomes how we can find a way to appropriately utilize these public samples and feed them to the server to verify model accuracy and computation correctness. To that end, we propose a novel technique named mix and check, which forms our technical foundation and allows us to meet all 3 design goals. The main idea of mix and check method is to let the client mix a set of public samples together with the samples to be queried and use them as inputs for executing privacy-preserving inference. In this way, These public samples are used to force the server to correctly perform computations by using a high-quality model as input. In other words, we can verify the model accuracy and computation correctness simultaneously without using expensive cryptographic techniques. For example, if the server uses a low-quality model or does not follow protocol, the client will observe inconsistent results across some of the copies or many incorrect inference results on public samples. And then, based on our newly proposed mix and check method, we designed a new maliciously secure inference protocol resilient to malicious servers named Fusion. In summary, Fusion has three main steps. First step, mixed dataset preparation. Second step, secure inference using synchronous inference protocols. And third step, client's local checks. Next, we would like to present Fusion in details. We assume that before the server and the client run Fusion, the server trains the model and the user provide inference services. The client has some query samples and pre-collects some public samples with known labels. Next, the client duplicates each query sample for big copies and then use random permutation to shuffle all public samples and copies of all query samples. The server and the client jointly perform inference computations using efficient synchronous secure inference protocols like cheat, FreeFlow2, etc. For every sample in the mixed dataset, the synchronous 2PC-based inference protocol is invoked to obtain an inference result. Finally, the inference results on all samples in mixed dataset are only revealed to a client. Fusion provides flexibility in choosing the 2PC-based synchronous inference protocols. Given those are known protocols, we omit the details here for brevity. When obtaining inference results on mixed dataset, the client checks the model accuracy and computation correctness by using simple but effective local checks without using expensive cryptographic techniques. The random shuffle of query samples and public samples is easy to design and implement. In the following, we would like to discuss how to select optimal numbers of copies and public samples. First, a necessary requirement is to ensure security requirement. That is, we should ensure that a server cannot successfully trick a client into believing that incorrect or low quality results are correctly produced by a high quality model. Second, in order to achieve the best efficiency, another goal is to pick concrete numbers that minimize the cost per query sample while satisfying the security requirement. We denote this requirement as the cost requirement. As such, we had to solve a parameter optimization problem that satisfies the security requirement, meanwhile meeting the cost requirement. We are now starting with security requirement. Well, security requirement states that the probability that a server succeeds in cheating is negligible. The events that a server can succeed in cheating includes, first, a server passes the model accuracy check of public samples. Second, the server also passes the consistent check of query samples. The inference results of all copies for every query sample are consistent, and inference results of some query samples are incorrect. For example, are produced by a low-quality model or incorrect inference computations. The probability of these two events happen are listed in equation 1 and equation 2, respectively. Given that the server can succeed in cheating when you can pass both checks, combining equation 1 and equation 2, the probability that the server succeeds in cheating is shown on the left. Let number be the statistical security number. A security requirement says that the probability server success should be no more than 2 to the power of minus lambda for every choice of these numbers. On the basis of satisfying a security requirement, another goal is to find optimal numbers that meet the cost requirement. We denote the average cost function for each query sample is shown on the right, and design optimization algorithm to search for optimal B and T. Our paper has more details. To achieve practical and privacy-preserving machine learning as a service, most of the related works have no alternatives but a set of less by adopting a weaker threat model. They assume that the server and the clients will follow protocol correctly, but they will also try to obtain additional information. That's semiotic security. Real world consider malicious security, which is normally expensive and inefficient compared to these of semiotic security. Although some solutions consider malicious security and guarantee computation correctness and preserve privacy, they do not verify model accuracy. Eventually, we would like to show the performance of Fusion. We compare Fusion with a state-of-the-art maliciously secure neural net inference protocol. Well, experimental results show that our Fusion can achieve great efficiency improvements, while we achieve additional verification of model accuracy. We also test the performance of Fusion by using several popular semiotic inference protocols as underlying building blocks, including ABY, Delphi, Queried, and Cheat. Our results show that cheat-based Fusion can have performance improvements by roughly 2 orders of magnitude when compared to those of using ABY and Delphi. We would like to understand whether Fusion can be more efficient when compared with semiotic inference protocols. We also compare Fusion with some semiotic inference protocols, and the evaluation shows that in some settings, Fusion can be more efficient than these protocols with weaker threat model. In addition, to show scalability, we conduct ImageNet-scale inference on a practical ResNet-50 model. It shows that Fusion can be faster and has lower communication in one setting than that of Queried. In conclusion, this paper proposes a secure and efficient inference protocol resilient to malicious servers, which can guarantee strong security requirements, meanwhile achieving high efficiency. Thank you very much for your time. This can close my talk.
Since the number of copies will affect the cost of Fusion, how do you choose that? So do you optimize with respect to that or what?
The number of copies when comparing Fusion with Leviosa, right?
Yeah.
A number of copies is 5 when comparing Fusion with Leviosa. To compare Fusion with Leviosa, we implement Fusion using cheat and adopted the same settings as Leviosa. Since Leviosa contains the computation and runtime of inference on 1,845 speech samples, so in our experiments, we'll also set the number of query samples as the same as theirs. When a number of total query samples is 1,845, we search and obtain that optimal number of copies as 5. When a number of public samples is 100. So, but average costs will decrease as the number of copies decrease. And if the total number of query samples is larger and will result in a smaller number of copies, Fusion can have greater performance improvements. Thank you.